go ahead and get started. So this is obviously the last lecture in the course before spring break, and it's covering material that is not going to show up on midterm 2 because you won't have time to practice with it. This is by design kind of an auxiliary lecture that will be helpful as a transition into the material that we'll talk about immediately after break. But it's unclear whether there'll be whether there will be more than perhaps 1 or 2 problems in the homework that maybe even 1 problem in the homework that will rely directly on this material. Nevertheless, I do think it's important to see this just to get the idea that that the space of algorithms that one can use to solve flow problems is actually part of a larger design space. There's a broader set of optimization problems that generalize flows. So you can think of the max flow problem and its dual, the min cut problem, as an example of this broader class. There's another problem that you've seen in 374 and earlier in some versions in 225 and possibly even earlier than that, the so-called shortest path problem, where you're given a graph with weights on the edges and a particular source node. You want to compute the shortest path from the source node to every other node in the graph. And it turns out that, in fact, both of these are special cases of something I apparently can't spell, minimum cost flows, which is mostly what I'm going to be talking about today. And then minimum cost flows are themselves a special case of a more general class of optimization problems called linear programming. And those are, in fact, I don't know if I want to say special cases, but at least there's a generalization of linear programming called integer programming. And I'm going to talk about linear programming in the week after the break. Now, the interesting thing here is this is the line above which generally things can be solved quickly in practice. In practice, there are tons of problems that can be formulated as integer programming problems or linear programming problems, or if you work really harder, minimum cost flow problems, or even shortest path problems. As you go up and down this chain of abstraction, as you consider more and more general problems, even though these things are practically solvable, the fewer assumptions you can make about the structure of the problem, the more difficult it is to get an efficient solution. Shortest paths are simple enough that we can explain Dijkstra's algorithm to people in 225. Maximum flows, we can explain Ford and Fulkerson and at least get the intuition that by choosing the augmenting paths carefully, you can get faster or slower algorithms, but we can't really explain the most efficient algorithm to you even in 473. For minimum cost flows, the most I can show you is there's some interesting structure here. And there's a generalization of Ford-Fulkerson, or actually a couple of them, that are the basis of how actual algorithms that solve these things in practice work. But we're a bit further away from the official solutions. Linear programming, again, I'm mostly showing this to you not because of the algorithms. I will show you the simplex algorithm if you've heard of that, but that's not the algorithm that works best in practice, and it's also not the algorithm that we know works well in theory. And then for integer programming, this is simply not the right department to be looking at practical solutions, because there's another line which is about here, where above that line everything can be solved in polynomial time, and below that line everything is NP hard. Meaning we don't believe that there is a polynomial time solution because there are too many hundreds of thousands of problems that if this one thing had a polynomial time solution, then all those other things would also have polynomial time solutions. And we've been staring at this brick wall for 70 years, and we can prove that we have no idea what we're doing. It's interesting that you hit the NP hard wall before you hit the practical wall. It's also interesting that really I should be probably doing this, because the polynomial time algorithms, or at least the earliest polynomial time algorithms for linear programming, are absolutely, decidedly not practical. The way that you get practical algorithms for linear programming is actually to sort of drag them up. There's a little bit of insight that you can get from the additional structure, but most of the algorithms where we can prove that things happen in polynomial time are not actually that good in practice. You are here. This is the right way to say this. We are here. I'll get to linear programming the week after, and then the week after break, so after we get through the midterm exam, we'll talk about integer programming, but it's mostly just going to be as an example of something that's NP hard. And we'll be talking about NP hardness. But I want to stick in your brain now is that as much as the standard line in theory is being NP hard means forget it, you're not going to solve it in practice, that's not actually true. The distinction is quite a bit more subtle than that. Okay, so what are minimum cost flows? So if you recall, the flow problem, you're given a source and a target, and you have various edges that carry certain amounts of flow. These are called capacities. Something that might look like this. Okay. And the goal is to push as much stuff through this system where I inject stuff at S and I extract stuff at T, subject to the constraints that whatever stuff comes into a particular node must be the same amount as the stuff that leaves that node. And at any edge, the amount of stuff that goes across that edge is between 0 and the number that's written on the edge. Okay? So for the standard flow problem, for max flow, edges have capacities. And we want to maximize the value of the flow. Okay? For the minimum cost flow problem, I'm now going to observe that there might be differences in an actual system for how you want to distribute the flow through the network. Right, so it's possible that, for example, I can send, you know, 5 trains an hour between Vienna and Graz, or I could send 5 trains an hour from Vienna to Budapest, and then those trains from Budapest to Graz. But I happen to know that the trains that go into Budapest all smell. Those soldiers don't want to ride those trains. There's a lot more desertions. You have to pay the soldiers more to ride those, whereas the trains that go from Vienna to Graz, the soldiers are happy to ride those trains because they smell nice and they serve beer at Wiener Schnitzel and everything is great. And so in addition to the capacity that you attach to the links between nodes, you recognize that sending traffic down some edges is more expensive than sending traffic down other edges. So for the minimum cost flow problem, edges also have cost. Okay, so when I talk about the capacity of an edge, I'm going to use C of UV to denote that capacity. When I talk about the cost of an edge, I'm going to use dollar of UV because cost also starts with C and C is taken. So hopefully this is mnemonic enough for you. And now what I want to do is minimize the total cost of the flow, which I'm going to define as the sum over all edges from U to V of the flow value through UV times the cost of sending 1 unit of flow through UV. Okay? This is the definition of the cost of flow F. Now, in both cases, I want a flow that satisfies all of the capacity constraints. There's a little bit of slack in the statement of the problem, which is that, and has maximum value. Right? So this is, if you like, a way of breaking ties between 2 different maximum flows. Okay. So I want the minimum cost maximum flow. Okay. Now, here's my flow network. So for example, I might say, sending any unit of flow down this edge is going to cost me $5. Sending any unit of flow down this edge is going to cost me negative $5. Meaning I'd really much rather send the flow down to the right than up to the right. Here, this edge might have a cost of 0. Let me just fill in -5 -$10 $6. Okay, so there is a flow network and with both capacities and costs on every edge. Okay. So I want to think back to the way that we solved the maximum flow problem, the way that Ford and Fulkerson works. And we've seen some variants of this, for example, in the last application of flows, where we wanted to cover a DAG with paths. There were different versions of this strategy. So the idea is, first, let me compute a flow that is at least legal. a flow that meets all of the capacity constraints, and let's not worry about whether it has maximum value back in. And then we observe by looking at the residual graph of that flow that we can identify places where we can improve the value by pushing flow along some path from S to T. And so the generic strategy for maximum flow algorithms is pick any feasible flow and then see if it's possible to increase its value while maintaining the fact that the flow is feasible. Okay? Now we're going to take that as a starting point for the minimum cost max flow problem. We say, okay, find any flow with maximum value, any maximum flow at all. And now, by looking at the residual graph, we might be able to identify some, easily identify some structure that would say, here is a way that I can change the flow to decrease its cost, but have the flow retain the same value and have the flow still be feasible. Okay. So we've got this sort of stack of objectives. First, I need to find a feasible flow. Then I need to improve the value while maintaining feasibility until it's a maximum flow. Then I need to decrease the costs while maintaining the fact that it's feasible and maximum. Okay? So let me start by assuming we've already computed a maximum flow, and then ask, what do we have left to do? Okay, so the general strategy is step one, find any max flow, and two, incrementally improve it. Okay. So let me take this flow network and put it down here, make it a little bit bigger so that I can actually write more stuff in here, and I apologize for this thing being a little bit crowded. And I'm just gonna run Ford Fulkerson here. I'm gonna push 5 units flow across the top. I'll push 5 more units of flow across here. 10, 10. I'll push 5 more units of flow across the bottom. And at this point, I've saturated all the edges coming out of S so that I now know this is a maximum flow. That's 10. That's 10. All the other edges have 0 units of flow. Okay? All right, so when I am talking about, looking for places where we can improve the flow value, we constructed a residual graph that encoded somehow for every edge how much more flow I can push either forward or how much flow I can subtract by pushing flow backward for that edge. Now I'm going to do the same thing in this case. I'm going to construct the residual graph using exactly the same algorithm, but for the new edges that I introduce into the residual graph, I also need to define the cost of pushing a unit of flow down those edges. Okay, so given the flow and the cost, I'm going to define, as usual, the residual capacity, C sub f from U to V. This is either the original capacity minus the flow, if UV is one of my edges, and it's the flow from V to U if V to U is one of my original edges. But I also need to define something called the residual cost. dollars of F UV. Anyone want to tell me what this is? So there are going to be two cases. So in this example, I've got 5 units. The residual capacity along this edge is 5, and the residual capacity along the reversal of this edge is also 5. So what is going to be the residual cost? How much am I going to change the cost, the overall cost of the flow, if I send one more unit of flow forward along this edge? Minus 10. What's going to be the effect on the overall cost of the flow if I send one unit of flow backwards? Plus 10. So how do I define the residual cost of an edge in my residual graph? So if UV is an edge in my original graph, the residual cost is going to be the original cost. If UV is the reversal of an edge in my original graph, then yeah, it's the negation of the original cost. Okay? Because sending one unit of flow down this reversed edge is the same as subtracting one unit of flow going forward along the original edge. Okay? So I get this much more complicated looking graph, which I am only going to draw a small piece of because it's going to take forever to do this. So for example, the edge going to T, I have an edge going forward and an edge going back. Each of the edges has 5 units of residual capacity. The forward edge has a cost of minus 10, and the backward edge has a cost of plus 10. Okay? All right. Now, I need to look for something in this new residual graph that would indicate I don't have the minimum cost flow in my hands. There's another flow with the same value, but has slightly lower cost. A circle. Okay, so let's. One way to think about this is we're not going to change. We're never going to change the value of the flow ever again. So the structure that we're looking to add to the current flow is a flow with value 0 in the residual graph. Right? Just like with maximum flow, you can say find any flow and then recursively find the maximum flow in the residual graph. The same idea is true here. Find any maximum flow, and then in the residual graph, find the minimum cost flow with value 0 in that residual graph. The flow with value 0 is a circulation. The stuff just moves around. Right? Now, any network has a circulation with cost 0, namely the one that all the flow values are equal to 0. Right? So what you're really asking is, can I find a circulation with negative cost in the residual graph? But any circulation is a sum of cycles. Just like any flow, we can think of as a sum of paths, and that's sort of how Ford-Fulkerson works. If there's available flow in the residual network, by the flow decomposition theorem, there'll be an available path in the residual network. The same thing is true here. If there's a negative cost circulation that can live in the residual graph, then in particular, somewhere there must be a cycle whose total residual cost is negative. Okay? So the basic theorem is F is a minimum cost flow if and only if this residual graph has no cycles And these are directed cycles with minimum total residual cost. Okay?
Negative?
Has no with, sorry, yes, minimum total, that's not what I wanted. Negative. Okay? So I'm not going to draw the residual graph here, but I'm going to point out, if I've done this right at least, there's a cycle somewhere perhaps here. The residual cost of this particular cycle is -10 for the edge on the bottom right, -6 because I'm going backwards along an edge that had cost 6 on that top right edge, -5 for that edge going down. This cycle also has, in this case, 5 units of residual capacity. I still have 5 more units that I can send along the bottom edge. I have 10 units that I can send along that top edge, and I have 5 units of capacity that I can send along the bottom. So because this cycle that I've highlighted has both capacity, all of those 3 directed edges appear in the residual graph because their residual capacities are greater than 0. And the total cost of those 3 edges is negative. This is an indication that this flow that I've described is not a minimum cost flow. So how would I reduce the flow cost without changing its value? Right, I push 5 units of flow around that cycle. Right? So instead of having 5 units here, this would become 10. Instead of having 10 units here, that would become 5. And instead of having nothing here, that would become 5. And then I would update the residual graph, including both the capacities and the costs. And in the new residual graph, I would look for another negative cycle. Okay? So the basic algorithm then is, again, I'm just going to repeat what I wrote before. Find any maximum value flow. And then 2, while the residual graph has a negative cycle, push flow around that negative cycle. And I should emphasize here that when I say negative cycle, I mean a cycle with negative cost. Okay. Now, this is actually not that far away from an algorithm you've already seen. Okay. So I want to show you, you can actually solve the original maximum flow problem using only step 2, right? Using an algorithm that you've already seen. So here is S, here is T. There is some flow network going on in between. I don't know what it is. And I want to compute a maximum flow from S to T in this graph. So the way that I'm going to do that is the following. I'm going to add a single edge from T back to S. I'm going to define the capacity of this edge to be infinite. And I'm going to define the cost of this edge to be -1. And every other edge in the graph, it retains whatever its capacity was that I got from the input, but I'm going to add to every edge in this graph a cost of 0. Sending flow across the edges in the original graph doesn't cost me anything. the only thing that I actually have to pay for is to send any flow back from T to S. And now you'll notice that for any flow from S to T, if I take any flow in this graph, right? So if I have some flow F that goes from S to T, I can turn it into a circulation by just adding F units of flow going across this return edge from T back to S. And the cost of that circulation is going to be minus the value of the flow. So if I want to find a maximum ST flow in this original graph, that's the same as finding a minimum cost circulation in this graph with the one additional edge, because the cost of the circulation is exactly the negation of the value of the flow. Now, there's exactly one edge in this graph that can ever have negative value in any residual graph. Because if I look at the residual graph of this stuff up here, the residual costs are always going to be 0. It's either going to be 0 because it's a forward edge, or it's going to be minus 0, which is 0 if it's a backward edge. This edge has cost -1. As soon as I start pushing flow around it, I might have this, direct edge from S to T, but that has cost +1. I'm not going to want to take it. So any negative cycle in this graph is going to look like this. It's going to contain the return edge, and then it's going to be some path from S to T. So this negative cycle canceling algorithm is Ford-Fulkerson in this case. Exactly the same. When I have exactly one edge that has negative cost, then finding a minimum cost circulation is the same as finding a minimum cost flow if I remove that edge from the graph. And the algorithms, there's a one-to-one correspondence. There's a mechanical correspondence between the various stages of the algorithm. And that also tells you how you would do the cycle canceling algorithm in this case. You would look at the residual graph and say, well, I need to find a cycle with negative cost. It's got to include this red edge. So I just need to figure out the rest of the cycle using whatever first search. Let me try to get from S to T. But don't use the return edge, the direct backward red edge that's there, because that doesn't count. In other words, it's exactly what you would do with Ford-Fulkerson. Right? So Ford-Fulkerson now is this negative cycle canceling algorithm. I suppose really I should say, it's a special case of the cycle canceling algorithm, because in general, in a flow network with costs, I'm not going to only have one negative edge. I'll have several. Right? But this at least shows you that this is not that different from the stuff we've been doing before. Okay? So in general, not when I'm not dealing with this special case, I need to find negative cost cycles. So in general, I have this step, finding a negative cost cycle. Now, in general, this is not going to be as easy as deleting one of the edges and using whatever for search. What am I going to do? How do I find a negative cost cycle? Bellmanford. So we've seen, very briefly, negative cycles before. So when we're talking about shortest paths, say, okay, it's okay to have some edges that have negative weights. Dijkstra's algorithm will either be incorrect or exponentially slow, depending on who you believe, me or Dijkstra. If you have negative edges, but it will work, at least for my version. But Bellmanford, the algorithm runs in a fixed amount of time and it returns the correct answers, even if there are negative edges, as long as there are no negative cycles. And the issue with negative cycles, if you remember, is that if I have a graph with some cycle that has negative value, the shortest path from S to T, or really I should say the shortest walk from S to T doesn't exist. There is no shortest walk from S to T, because I can always go around that cycle one more time and make the path shorter by 2. Okay. So negative cycles mean no shortest paths, basically. But as a consequence of this, it means that we can find negative cycles using a shortest path algorithm. Okay, so we run Bellmanford. If there are no negative cycles, Bellmanford is guaranteed to terminate after order VE time. And at that, if we run it to completion, and then we say, just as a sanity check, let me go through the graph one more time and see if I can find any more tense edges, any edge that seems to indicate I haven't converged to the right shortest path distances yet. And if you find an edge that is off, that is still tense, so for example, if I find this edge where this has a distance of 8, and on the other hand I have a distance of 4, I know I haven't converged because this 4 is the length of some path from S to here, and this 8 is the length of some path from S to there. But by going to this 8 and then the negative 5, I can actually get to here in only 3 steps. So I haven't converged to shortest paths yet. So by doing one extra iteration of Bellmanford, I can at least identify that there are negative cycles in the graph. And then with some modifications, I can actually compute that shortest path. So there's a modification of Bellmanford, which finds a negative cycle in order VE time. Okay. Now this is one big difference from Ford-Fulkerson, where in a single iteration I could do everything in linear time. I just needed to do breadth first search. Yeah.
How does this algorithm guarantee that you're going to get the minimum cost? Say for example, I have an edge which is shared between 2 negative cycles.
Right.
And we choose one of them, and then we rotate the flow along that graph, along that cycle.
Mm-hmm. But
then the capacity of the edge is now full, so that you can't do it on the other cycle.
Right.
But the other cycle might have lower cost.
So the correctness of the algorithm relies on the following observation. If there is a negative cost cycle anywhere in the residual graph, your current flow does not have minimum cost. And if your current flow, if there is no negative cost cycle in your graph, your current flow does have negative cost. So it's true that there may be 2 different cycles that are both negative, but one has a little bit more capacity than the other. So you might end up in a situation that looks like, okay, so here's the shared edge that you talked about, and there are 2 negative cycles that share that edge. So first I'm going to push flow around this one and say, oh, well, that was the wrong one. That was the cycle that used up the middle edge, but it was not. The other cycle actually had more negative cost, so I should have pushed flow the other way. What will happen is this will show up now in the residual graph because you pushed flow around that blue edge. That means the backward path is going to show up. And now this is a negative cycle. Because the cost of this cycle is the difference between the original blue cycle up here and the original blue cycle down there. And you told me that this one was the one that was more negative. So that means this purple thing is actually still going to be negative. But good question. Okay. All right, so this is how to do one iteration. So now the question is, how many iterations? How many times do I need to do this? And the situation here, not surprisingly, is exactly the same as it is with Ford-Fulkerson. If I make no assumptions about which negative cycle I pivot around, and I make no assumptions about the capacities and the costs, whether or not they're integers, then I have no upper bound. I run forever. I may not converge to the minimum cost flow. I really don't have an algorithm here. But if I assume that I have integer capacities and I have integer costs, okay, let me assume both of these, then each iteration reduces the cost of the current flow by at least 1. Because when I find a negative cycle in the residual graph, the capacity of that cycle is at least 1, because it has to be an integer and it has to be none. It has to be positive. So I'm sending at least 1 unit of flow around this edge of this cycle. And because the costs are integers, the cost of sending 1 unit of flow around that cycle has to be at most -1. It has to be negative and it has to be an integer. So the most it can be is -1, which means the total change in the flow is in the cost is at least 1. And so that implies that the number of iterations is at most, and this is horrible, we need a crude bound on what the absolute minimum cost you could possibly get. Okay, and so this turns out to be something like C times D, where C is the sum of all the capacities at the edges, and D is the sum of the absolute value of all the costs at the edges. Okay. This is really awful, but it's something. It's something finite. Okay. Now, oh, sorry. Yeah, that's right. Yeah, close enough. Okay. Now, just like with Ford-Fulkerson, there are different choices that you can make about which cycle to go around. The one that you actually want to go around is what's called the minimum mean cycle. So what this means is you look for a cycle where you might think, I want to take the cycle that has minimum cost. Out of all negative cycles, take the one whose cost is furthest away from 0. That doesn't actually work out because there might not be much capacity on that cycle. You might think, let me find the negative cycle that has the maximum amount of capacity, but that might not work out because the cost might be too small. So what it turns out, the right thing to do is to find the cycle where you minimize the cost of all of the edges along the cycle divided by the number of edges in the cycle. Sorry, that should be C. All right, so if I have a cycle C, the mean cost is you take the total cost of all the cycle around the cycle, you divide by the number of edges. And again, there is a somewhat more complicated version of Bellmanford that will find the cycle that minimizes this objective in order VE time. And then the overall running time of the algorithm is something like VE squared log squared V. Okay. Too much detail to go in through, especially in the last lecture before spring break. Okay. This seems to be the best choice if you're going to use this particular algorithm. Okay? Yeah. No, this is not assuming anything about integers. This is purely combinatorial, purely algebraic. I mean, I've described the algorithm to you. You repeatedly find the cycle that minimizes this cost. That takes you order VE time. And then the difficult part is to show that after E log squared V iterations, you've converged. Okay. So this is not the only way to solve this problem, right? And mostly because this is going to be important when I'm talking about linear programming, I want to show you a different way of thinking about how to compute minimum cost flows that is in some sense a mirror reflection or a dual of the algorithm that I'm showing you here. Okay. Before I do that, though, I need to stop and make sure that people are kind of on board with what we're doing. Yeah.
Is that number of edges or number of
This is number of edges in a cycle, capital C. Sorry, this capital C and that capital C are not the same. So maybe it would be better if I just wrote it out in English. Total cost of the cycle divided by the number of edges in that same cycle. Right. Yeah. I'm sorry? Which condition, if and only?
So the whole thing relies on that if and only, right? So you need to find a negative cycle that you reduce find minimum cost.
So no, we haven't gone through the formalities of the proof. I'm going to claim that and allow you to trust me that you don't actually want to see the formalities of the proof. It's not that different from the min cost, the max flow min cut theorem proof. The basic argument is if there were a flow with smaller value, you look at the difference between the flow you have and that flow with smaller value. That difference is going to be a feasible circulation in the residual graph. It's going to have negative costs, and therefore somewhere in there's going to be a negative cost cycle. Okay. So at the very beginning, I mentioned another problem that also can be thought of as a minimum cost flow problem. This is the so-called shortest path problem, which you all know and love because you've probably implemented it. Let me try to show you why you can think of that as minimum cost flows. Okay, so here is my vertex S, and I want to imagine that I have some graph, and I want to compute shortest paths in this graph. Okay, so a graph, a cost on the edges, or in this case, lengths, if you like, on the edges, some of which are positive, some of which are negative. I'm going to compute shortest paths. Okay. So I'm going to do the following weird thing. I'm going to consider a version of flows where instead of always having to have balance 0 at every vertex, I'm allowed to have non-zero balance, but I get to specify that balance in advance. Okay, so if I set up balances at every vertex, B of V, what this means is that in any feasible flow, the sum of the flow values coming into V minus the sum of the flow values going out of V must be equal to this number that I've specified as my balance. So in the traditional flow problems we've been playing with, this number is always 0. Okay, but let me step back away from that. I'll show you in a second that you can reduce this back to the original kinds of problems. Okay. And so what I'm going to do is, in this shortest path network, I'm going to define every node to have a balance of 1, except the source, which is going to have a balance of 1 minus V. And now, one of the conditions that you need to have on these balances in order for them to make sense is that the sum of all of the balances has to be 0. Right? Because what you're doing is you're taking, well, I take all the flow into V and subtract all the flow out, and then I take all the flow into W and I subtract all the flow out, and I take all the flow into X and subtract all the flow out, and I do that for every vertex. Every unit of flow was added once and subtracted once, and so the total is going to be 0 everywhere. Right? So what I'm establishing here in this network is every node except S has 1 unit of demand, and S has V minus 1 units of supply. Okay? So instead of some indeterminate amount of stuff coming in at S, I know exactly how much stuff is coming in at S, V minus 1. And instead of that same indeterminate amount going out at T, in this case, it's all spreading out through the network. Okay? Now, let me think of the cost of each of these edges to be the weight that was input originally. Okay. And then finally, I'm going to set the capacities of each of these edges just to be infinite. I don't care. I don't have a limit on how much flow I'm going to send. And now, imagine, if you will, what happens when I compute a shortest path tree. Okay? Assuming there are no negative cycles in this graph, all of the shortest paths coming out of S to all of the other vertices are going to define the tree. So that tree might, for example, look like this. Can you actually see that? Maybe not. Let me try using a different color that's a little brighter. Okay, so here's a tree. This is the shortest path tree. And what I want you to imagine now is I can take the shortest path tree and imagine it as carrying a flow. So I've got V minus 1 units of, let's say, I've got V minus 1 Barbie dolls at S, and every other node says, I want a Barbie, give me a Barbie. And so node S says, great, just send the Barbie along the tree to the other node. Okay? That's a flow. Right, so how much am I sending? For example, there's going to be one, whoops, sorry. There's going to be one Barbie going down that edge because it goes to the leaf and then it stops, and that one node has a Barbie. There's going to be 2 nodes, 2 Barbies going down that edge. One of them is going to drop off at this node on the far right, and then the other one is going to go down. There'll be 3 Barbies going along this edge along the top. And in general, 1, here's 2. There's going to be a total of 6 Barbies going along this edge and 1 Barbie going along that edge. Okay. So the shortest path tree you should really think of as a flow. Stuff comes out of the source and wanders out to all the other nodes in the graph. 1 unit every time that it passes a node, it drops off a Barbie. It says, here's your Barbie. Okay? Until it eventually gets leaves and it runs out. Now, I can turn this back into a traditional minimum cost circulation problem. Move this down a little. By just adding edges going back from all of these other nodes back to the source, each of which has a capacity of 1. And each of which has a cost of 0. Okay? So the cost of 0. Yes, I believe that's true. And now when the Barbie, instead of going to S, the Barbie goes out to the other node, at the end of the day, mom says, give me the Barbie back, and puts it back in the toy box. Okay? And now I claim that if you push through the analysis of the residual graph stuff, in this case, you'll observe that this is in fact not just any flow, not just any circulation, if I added the 1 unit of flow back along those return edges, but actually the minimum cost circulation in this network that's feasible. Yeah, that's feasible given those capacity constraints. Right. So maybe I should approach this from the other direction. Take a regular minimum cost flow problem and recast it in a way that makes it look like I'm solving the shortest paths. And maybe we can sort of intuitively meet in the middle. I don't want to go through the details of this reduction because I didn't prepare them in advance and I don't want to improvise. Apologize for that. But at least I want to give you the idea that you can think of shortest path trees as flows. Yeah.
So for the minimum cost, we have this idea of a node S and a node T, but now it seems to be changing it so that there's just one node S and there's no.
And there's lots of nodes, each of which is a little t. All right, so instead of all the flow going from one node and then spreading out and then converging again, where it all goes out, in this case, the flow is starting at a particular source and flowing out, and at every node, a little bit leaks out of the system.
Why actually want to go back to S instead? I thought you're gonna put a T there and want them to all.
I could have done it that way too, and then turn it into a minimum cost flow.
Yeah.
By sending it back to S, I'm turning it back into a minimum cost circulation, which is what we use to compute minimum cost flows anyway. Right? So, I mean, what you're starting to see here is that there are lots of ways to think about what's going on. And in general, when you're in a situation like that, the more different ways you can comfortably think about the problem, the better you understand it, because you can switch from this set of intuition to that one on the fly as it's convenient as you're designing your algorithms or thinking about correctness or thinking about efficiency. Right. So I really want to think of minimum cost circulations as being maybe the reference problem for at least the next few minutes, rather than minimum cost to maximum flow. So let me go from the other direction, and let's suppose I have, consider a, min cost circulation problem. Okay, so I have a graph G. I have capacities C. I have costs. Don't recognize a dollar sign. Okay, and some of the costs are positive, some of the costs are negative. I want to find the circulation of minimum total cost. And the traditional way, the way that we've been doing this so far, is find any circulation at all. Well, that's easy, just put zeros everywhere. And then improve it to the point where there are no more negative cycles. Okay? So, in the past, we said find any circulation and then remove negative cycles. Okay? And when I say circulation, what I really mean is I want to satisfy the balance constraints. I want some function on the edges that satisfies the balance constraints. Again, this is easy because I can just plug in 0 everywhere. And then I'm going to reduce the cost, but maintain the fact that the balance constraints are always satisfied. And the way that I'm going to do that is find negative cycles, and I'm going to remove them one at a time. Okay? Now I'm going to change this. Now, I'm going to remove all the negative cycles. And then I'm going to restore my balance constraints by, again, making incremental changes to the flow that I've constructed in the first step. Okay? So the very first thing I'm going to do is I'm going to look at my network and say, I can make the following change to reduce all the negative cycles by assigning some function to the vertices. But when I do that, I'm not going to satisfy the balance constraints. But I'll know, at least when I'm done, there are no negative cycles. And I'm going to retain this condition that there are no negative cycles, and then change the flow, I don't want to call it a flow, change the function that I'm storing, the pseudo flow, if you want to call it that, to sort of get closer and closer and closer to restoring the balance constraint. And when I'm done, in both cases, I have a function that satisfies the balance constraints, whose residual graph has no negative cycles. And the claim that I made earlier was when I'm in that situation, the flow that I'm holding is the minimum cost circulation. I'm sorry?
How do you prove these things? Does it actually converge?
We'll get there. We'll get there. Okay? So the first question is, how do I remove all negative cost cycles? Okay? So let me draw a much, much simpler graph. And I'm only going to put in, for the moment, the costs. There are capacities in this graph as well, but for now, let's just think about the costs. Okay. Now, somehow I want a way of removing these things. So actually, let me go ahead and put in the capacities of these edges. Okay, so the blue, those are capacities, and the green, because they have dollar signs on them, those are the costs. Okay? How do I set up something that kind of feels like a flow that is guaranteed to have no negative cycles in the residual? It's a little weird because we're deliberately not enforcing the balance constraints. And so I'm asking you to cheat. How could we cheat? Yeah?
Fill up all the capacity of all the negative edges.
Yes, exactly. So I'm just going to take these two negative edges, and I'm going to push as much flow down them as I can. Now, never mind that the 6 units of flow I want to send down this edge don't come from anything. They're just magically created at this node in the upper right, and they magically vanish at this node on the upper left. Likewise, the 5 units of flow down here are magically created and magically destroyed. Never mind. That's you're worrying about the balance constraint if that concerns you, and we're deliberately allowing you to violate that. Okay, so I'm going to send 6 units of flow down this edge, 5 units of flow down this edge, no units of flow down these 2 edges because they're positive. And now let me look at the residual graph. Need to make this a little bit bigger. Okay, now I'm going to have edges that look like this. Now in my residual graph, because I've saturated that edge, essentially this is the same as flipping the edge in terms of capacity. I've got 6 units of capacity here, 5 units here, 3 units here, 4 units there. And whenever I flip an edge, I negate its cost. So this is still going to have negative, 5, 3. But now the cost of this bottom edge is +2, and the cost of this top edge is +10. But there's in addition to residual capacities and residual costs, I have another thing that I need to record in the residual graph, which is residual balance. Somehow in the stuff that I add to this function, I need to add 6 more units of incoming flow to this vertex up here. This vertex has a demand of 6 in the residual graph. And the vertex in the upper left has a supply of 6, or demand of -6. In the bottom, I have a supply of sorry, not 2. I have a supply of 5 and a demand of 5. Okay. So saturate all of the negative cost edges, and then compute the residual graph, which involves residual capacities, which are really just the same as the original capacities. Residual costs, which are either the same if those are positive, or they're negated if those were negative. And when I negate, I also reverse the edges. And I have residual balances, which say how much more flow I need to send into this vertex than I send out. Okay? Saturate all negative edges. And then I compute the residual graph with residual balances, in addition to residual costs and residual capacities. Okay, now somehow I want to improve this. I want to improve the function that I've applied to the graph over here on the left by looking over here on the right and finding something that will make things more balanced but will not introduce negative cycles. Okay? Any guesses? How would, forget for the moment about negative cycles. If I saw a graph like this, what would be the thing you were tempted to do? This has a supply of 5, this has a demand of 5, this has a supply of 6, that has a demand of 6. How should I try to meet those supplies and demands? How do I match them up? Right, find some demand and ship it to some supply. Or, sorry, find some supply and ship it towards some demand. Okay, so the positive things have supply, the negative things have demand. In this case, there doesn't appear to be anything I can do. The other way? Oh, I wrote demands. Okay. Supplies are negative, demands are positive. Good. So I need to find some supply and I need to ship it to the demand. Okay. So, but how am I going to ship it to the demand? I mean, in general, in this particular example, it may be a little bit too simple. But in general, what I'm going to end up with is I'll have some node over here that has some supply, and I'll have some other node over here that has some demand. And I somehow want to get stuff from here to there. And I want to do it in a way that doesn't create any negative cycles. Okay, forget the negative cycle thing for the moment. How would you propose that I ship stuff from this node to that node? Efficiently. What did you say? DFS? Well, DFS tends to find really long, rambly paths, and it's not quite going to be the right thing.
Whatever happens.
Right, but the problem is, if you wander from this node to that node along just any old path, the problem is that when you now look at the new residual graph, you might have just introduced a negative cycle. Okay? What that negative cycle means is instead of going around the path one way, it would have been cheaper to go around the path a different way. So what I want is to find the cheapest path from the supply to the demand. Okay. Another way of saying that is I want to find the shortest path from the supply to the demand. So I pick any node that has supply. I pick any node that has demand. I compute the shortest path from the supply node to the demand node, where the weights of the edges are defined by those residual costs. Now I have a path that I can push flow along. I push as much flow as I can. And there are three things that might happen. One is I might actually exhaust the supply, and this node is now balanced. That's good. One option is I might exhaust the demand, but still have some supply, but still I've got one node that's more balanced, and that's good. A third possibility is that when I push flow along the shortest path, I might saturate some edge in the middle, but that's still better because I've exhausted some of the supply, and I've met some of the demand. So the total supply is going to go down no matter what, and the total demand is going to go down no matter what. Okay? So the algorithm, which is usually referred to as successive shortest paths, is find any node U that has a residual balance that is negative, any node V such that the residual balance of V is positive, and then push flow along the shortest path from U to V, where shortest is defined with respect to the residual costs, and the amount of flow that you push is limited by the residual capacities. Computing the shortest path you can do in order VE time using Bellmanford. You might have to use Bellmanford because after you've done one iteration of this, you're going to have residual edges with negative costs, but never negative cycles, so Bellmanford is always going to work. This shortest path you can always find in order VE time using Bellmanford. And then there are questions about how many iterations it could take. But you notice that if all of your supplies demands when you start this process are integers, and all your capacities are integers, then every iteration you're going to exhaust at least one unit of supply. You're going to need at least one. Right, well, I mean, all this is happening inside the residual graph, which means you're just describing how to add on to that first function that you computed. Again, it's just like for Fulkerson. You compute something, and then you figure out how to finish it by recursively solving the problem in the residual graph.
You said any node there, so you could set 5 back to 5, 6 back to 6, and you get back to your original graph.
It is possible that you could get back to the original graph. If you do that, it's because the minimum cost circulation in the original graph is the one that has zeros everywhere. That may very well be the correct answer. It's quite possible that the correct answer to this minimum cost circulation problem is don't send anything anywhere. It's possible. In which case, this algorithm might do a bunch of work and eventually return back to the zero function. Okay, clearly this is not the best way to get nothing. But if nothing is the correct answer, then that's what it should do.
I mean, in the description, you say choose any node that has 5, choose any node that has that.
Yes.
Demand. So you could potentially choose the one with -5 with 5.
Yes.
And you find the shortest path, positive minimum.
Yes.
You actually send those things back.
Yes.
Which means you actually go back to your original graph. But from your original graph, that is not the shortest path. Right? I mean, that is not the best solution here.
So you're right. For some input instances, you might end up going back to the original thing. If you end up back at the original thing, then the answer is the all zeros flow, and that's correct.
But this one is not, right?
And therefore, that is not where you will end up. You will not end up meeting all the demand back here if I've set it up correctly, which is it's quite possible that I haven't set it up correctly. Okay. The best algorithm that uses this idea runs in this much time. And of course, it's due to Orlin. And it's complicated. And that's as much as I want to say about minimum cost flows. Thank you for staying 3 minutes after, especially in the last session before break. Please have a relaxing, enjoyable break. Come back ready to finish the semester.